Hello, everyone, and welcome back to Math Zone African Motives. I want us to continue with our preparation for our March test. So today I brought you a question paper that is for grade 11 physical sciences. And that question paper is coming from the Limpopo province. It was a controlled test that was written in March 2024. So I want us to use this question paper to prepare for our March test. So you will see that this question paper is made out of two sections. The first section is multiple choice questions. That is out of 10, and they carry 20 marks. And then the second section is structured question, which is section B. And when it comes to structured question, that is where you have got the majority of your marks. So on your multiple choice questions, you'll be given 4 options, which is either A, B, C, or D. And out of those 4 options, there will always be only one correct answer, which is the most accurate answer out of these options. So you need to choose your answers in accordance, meaning to say that you have to choose the most accurate one. And guys, let's stop that culture of guessing. I know most of you, when it comes to multiple choice questions, you usually guess. But let's use all of the laws that we have learned in our classes, as well as all of the concepts, the notes that we were given, to try and reason out with the answers that are given so that we can be able to choose the most accurate. So without wasting time, I would like us to start with question number 1.1, which was saying, the force exerted by a surface on an object which is in contact with it and x perpendicular to the surface is called what? So we have got an object, and then there is a surface that is in contact with this object. And they are saying that surface applies a force to this object. And that force, they are saying that it is perpendicular to the what? To the surface of that. What is this force that is applied by that surface? We know that that force becomes what? Our normal force. So our answer here was going to be D. So our answer here, it was going to be what? To be D. Now, let's look at question number 1.2. Question number 1.2 is saying, the gravitational acceleration on the surface of a planet of radius r is G. The gravitational acceleration at a height of 3r above the surface of the same planet is what? So initially, we know that the force due to gravity can be given by gm1 m2 over r squared, where this is the same as the what? As the weight of the planet, given that we know the mass of the planet as well as the what? Gravitational acceleration. Now, we are told that the gravitational acceleration on the surface of a planet of radius r is g. So now, I would get to assume that the mass of the planet, or else the mass of the object that would be on the planet, would be the same. So now, our g would be given by g m2 over r squared. So let's assume that we are saying that the mass of the what? The mass of the object on the same planet would be constant. So we remove that mass. So m1 would be equal to that m1. So the gravitational acceleration now of this object on this planet will be given by this constant times the mass of this planet all over what? R squared. Where now this r squared is this r. So here I would be having what? G m2 over r squared. That is the gravitational acceleration on the surface of the planet that is having a radius of r. What if now we are now looking for the gravitational acceleration at a height of 3r above the surface of the same planet? Now, when we are at a height of 3r above this, it simply means that our r, it's now equal to this r, which is the what? The radius of the planet, plus 3r, where we are, the distance above the planet, so that the distance from the center of this planet to where we are would be equal to what? To 4r. Now, our new g, which is our new gravitational acceleration, will now be given by g m2. Then now, where I'm having this r, I'm going to replace with 4r. So I will have 4r squared. And this will give me what? It will give me g m2 all over 16r squared. So we can actually get to see that I can now factor out this to be equal to that. So here I would be having g all over what? All over 16. So our answer there was going to be what? Was going to be A. Our answer there was going to be A. At some point in time, this to others might not be as clear as it's supposed to. So I'm saying that our new r is now equal to the radius of the planet plus the distance above the surface of the planet. That gives us 4r. So this is the distance from the center of the planet to where the object would be. Now, the new gravitational acceleration will now be given by g m2 all over r squared, where now this r that we are having here would be replaced by 4r. So it would be g m2 all over 4r squared. So now the new g will now be given by g m2 all over 16r squared, which is the same as 1 over 16 times g m2 all over r squared, where we have seen that this represents what? G. So I would come here and substitute g there. So I'll be having 1 over 16 times our g, which is the same as saying g over 16. So that is how I now managed to calculate my new what? Gravitational acceleration. That's why we say the answer becomes what? G over 16. So now let's go to question number 1.3. Question number 1.3 is saying the mass of a man on Earth is 85 kgs. What will the mass of the same man be on the surface of a planet which has the same mass as Earth but half the radius of the Earth? We know that mass of an object does not depend, it does not depend on the location of the object. It does not depend on location. When we say location, we are saying that if a man is having a mass of 80 kgs when he is on Earth, even if he goes to the moon, the same man would be having a mass of 80 kgs, 85 kgs. So the mass will always remain constant. So mass is constant regardless of where we are. Mass is constant regardless of where we are. Why? Because mass is a measure of the total amount of an object. So we are always going to have the same mass. The mass will not change. Now let's go to 1.4. 1.4 is saying an object placed a distance r from the center of a planet experiences an attractive force F. Which one of the graphs below represent the relationship between the force F and the distance r from the center of the planet? So the force F is the what? Is the force that an object that is at a distance r experiences is due to the attraction of what? Due to the attraction to the center of the planet. So this force is the one that we know that it is equal to what? G m1 m2 over r squared. And the relationship between F and R is given by F is directly proportional to 1 over r squared. So if F is directly proportional to 1 over r squared, it means that if I draw a graph, I'm saying that when my F and my 1 over r squared is like this, I'm saying whenever my F is increasing, or else let me say that my F is the one that would be dependent on what? On R. So I would come and say, whenever my R is increasing, my F has to increase. So you will see that you would have a linear relationship that is going that side. To say that whenever my 1 over R squared is increasing, my F will also be increasing. That is coming from this relationship. So we are looking for a graph that looks like this. And that graph becomes B, where we are saying that whenever our 1 over R squared is increasing, our F has to increase. That's why we've got a linear relationship like that. So that becomes our answer there. So we know that the gravitational force of attraction to the center of the what? Of the planet is always directly proportional to 1 over what? R squared. But it is inversely proportional to what? To R squared. It is inversely proportional to R squared, but directly proportional to 1 over R squared. That's where people need to actually give a what? You need to actually be able to differentiate there. So that was our answer there. Now, I think I just went on to question number 1.6 by skipping question number 1.5. So let's try to see if 1.5 is below there. Yes, we have got 1.5. Now we are now saying, we now have got 3 forces. So they are saying 3 forces acting on an object are in equilibrium. Which one of the vector diagrams below indicates the forces in equilibrium? So a vector diagram that represents forces that are in equilibrium should be a what? A closed. We should have what we refer to as a closed vector diagram. So a closed vector diagram, it represents forces that are in equilibrium in such a way that F net would be equal to 0. So what do you mean by closed vector diagram? Let's say I've got F1 in that direction, and then F2 in that direction. Now, I will now need to have my F3 closing that vector diagram like this, so that my net resultant force, which is equal to the sum of F forces, would be equal to 0. So I would have this going that side, and then my final force has to close that diagram. That is what we are simply looking for. That is what we call a what? A closed vector diagram. So you can see that this one starts going that side, but already now I'm having something opposing it. So this is already out. And then I go to B, F1 goes that side, and then F3 goes that side, F2 is going that. So I can see that I'm starting here, I go through, and I'm ending where I started. That is what we mean by a closed vector diagram. It's as if I'm having a circle like that. I have to end where I've started. So if I started here, I have to end here. So this is what you are seeing. The arrow is pointing that we are going in this direction, and then we are going in that direction, and then we are going in that direction. So we are ending where we started. That is what we mean by a closed vector diagram. So that becomes B. So our answer there was going to be B. Whenever our forces are in equilibrium, we've got our net force being equal to 0, and our net force being equal to 0 is represented by a closed vector diagram. Let's go to 1.6. Now 1.6 is saying 3-point charges of magnitude 2 microcoulombs, which is a positive, 3 microcoulomb, which is a positive, and 3 microcoulomb, which is a positive, are placed in a vacuum to form a right angle triangle as shown in the diagram, or else to form a right angle. So I've got positive 3, positive 3, positive 2 microcoulombs. The net force acting on the positive 2 microcoulomb can be represented by what? So the net force, or else let me say the force due to this on this, the net force due to the 3 microcoulomb on this would be a repulsion force. So these two are going to repel. So what it simply means is the 3 microcoulomb is going to push the 2 microcoulomb going up. And also this 3 microcoulomb is going to push that 2 microcoulomb going to the right. So if I'm to take these forces and maybe get to resolve them in such a way that they are like this, as we know our vector diagram, and I try to find my resultant, I'll start from the head of my first what? Of my first vector and end at the tail of my last vector. So that becomes my what? That becomes my resultant. That becomes my resultant. So my resultant here would be given by something like this. So that becomes my resultant. So now they are saying the net force acting on the 2 microcoulomb can be represented by what? This resultant becomes my net force, because we are saying net resultant force. Now the answer becomes D. The answer that corresponds to this becomes D. Let's go to 1.7. So 1.7 is saying two identical spheres, R and S, on insulated stands carrying charges of positive Q and negative Q, respectively, are placed a distance R apart. These are the positive and negative charges or spheres. Sphere R, which is this one, exerts an electrostatic force of magnitude F on sphere S. So we already know the force that is being exerted here. So for R exerts a force of F. The two spheres are now brought into contact and are then retained to their original what? Are then returned to their original position. So now, the magnitude of the electrostatic force that sphere R exerts on sphere S is. So these two are brought together. When they are brought together like this, these two will now, guess to what? They will now have a total charge that we are saying is equal to the what? To the sum of the two. So we are going to have sum of the what? Of the individual charges. So if a total charge is going to be equal to what? Positive Q plus a negative Q, that is equal to 0. When they are separated now, they are going to have a new charge for each, which is equal to what? To total charge divided by 2. That is going to be 0 over 2. And if the new charge for each, that is the new charge for R as well as the new charge for S, is equal to 0, what is the magnitude of the electrostatic force that sphere R now exerts on S? We know that the magnitude of F would be given by K, Q1, Q2 over R squared. And we are saying that this, that we can actually get to say K, Q squared over R squared. This charge is 0. So I would be having 0 over R squared, which is just equal to 0. So the magnitude of that force, is supposed to be equal to what? To 0. Why? Because the new charge is now equal to what? To 0. So my answer there, was going to be C. My answer was going to be C. My answer was going to be C. Because this is where I've got my F being equal to what? To 0. This is due to the new charge of the two spheres after separation, after they had been brought together. Now let's go to question number 8. Consider the following vector diagram and answer the question that follows. This is the vector diagram. Which one of the vectors is the resultant of the other three vectors? We say that the resultant starts from the what? From the head of the first. And then it ends. The resultant ends at the tail of the last. So we are looking for a vector that is starting at the what? At the head of the first and ending at the tail of the what? Of the last. So you can say that this is starting here and then it is ending there. So this is starting at the head and ending at the head. Starting at the head, ending at the head. Starting at the head, ending at the head. Sorry, this is now ending at the what? At the tail. But you can see that this is starting from the what? from the tail to the tail. We are looking for something that is starting from the head to the what? To the tail. And that is W. So this becomes our resultant because our first vector is that one, second vector is that one, third vector is that one. So we are moving in this direction, moving that direction, moving that direction. If we're having a vector that is going this side, it will be a closed diagram. And our net resultant force was going to be equal to 0. Or else our net resultant vector was going to be equal to 0. But now we are not having a closed diagram. So this one is the one that is representing our what? Our net resultant vector. So W, which is equal to C there. So just know how you find resultant. You need to go back and revise how you do find resultant vector when you are given a what? A vector diagram. You need to use the head to tail theorem. Now 1.9 is saying a girl which has a weight of 600 Newton is standing on a bathroom scale in a lift. So we are saying that there is a girl who is standing on a bathroom scale. So we have got a girl who is standing on a bathroom scale, and the reading here is 600 newtons initially, and we are in a lift before the lift starts moving. A girl which has a weight of 600 newton is standing on a bathroom scale. So the 600 newton is the weight of the girl before any movement. Now they're saying that she is in a lift that is moving. Now the lift is now moving. She noticed that the scale now reads 660 newtons. Now the scale reading is now equal to what? 660 newtons. What is happening here? Which one of the following is the correct conclusion about the motion of the lift? Is the lift accelerating upwards? Is it accelerating downwards? Or else, is it moving at a constant velocity? What is happening? We know that when the weight of our girl is equal to 600 newtons, there is no what? There is no movement. So acceleration is equals to 0. When now the weight is now greater than 600 newtons, there is now acceleration because there is a net force there. And that net force is equal to the difference of what? Of 600 and the new recorded what? And the new recorded scale. And now you can see that it is 660 minus 600, which gives you a positive 60 newtons. So that positive should tell you that the lift is accelerating upwards. Why? Because this tends to oppose the weight of the girl. Once we are opposing the weight of the girl, it's as if we are now saying that. It's as if we are now saying that. It's as if we are now saying that the weight of the object is the one that is opposing the what? The motion of the lift going up. So the weight now, it now needs to be what? Whenever we now have got the weight of the object being 660 newtons, it means that the lift is going what? Is going up. Because this weight is opposing. So as it is opposing, when there is an increase in this value, it means that our opposing force is the one that is greater than the weight. If that is the case now, we are looking for what? Acceleration upwards. We are looking for acceleration upwards. Okay. Maybe someone might say that I did not get what you said, my guy. I said that initially, when the scale is 600 newtons and the girl is on top of the scale, that becomes our weight, which means that our F net is equal to 0. That's why we are having a scale reading of 600 newtons. Once there is a difference in this scale reading, it means that we now have got a net resultant force, which might be equal to F1 plus F2. Now, you can see that there is now a new force which is 600 newtons. So that 600 newtons has to give a net resultant force. So we need to now say 660 minus 600. That gives us a difference of 60 newtons. So we are saying that this 660 is in the opposite direction to our original scale reading. And our original scale reading is going that side. So it means that the direction that is opposite to this one is going up. So that is how you can also get to decipher what? To say that my lift is accelerating upwards. We are having a positive what? We are having a positive difference there. So it is moving in the opposite direction. That is how you can also get to choose that answer. Passengers in a moving car are advised to wear safety belts. This will reduce their chances of getting injured in the event of an accident. So we have got a car. With that car now, a passenger who might be seated there is advised that she should wear a safety belt, or else he should wear a what? A safety belt. The safety belt would be providing a force that is going that side. So a safety belt provide the force of the what? Of the safety belt going that side. And the car motion is in that side. And they are telling us that this actually prevents us from getting injured. How does it prevent us from getting injured when there's an accident? Whenever there is an accident, let's think of maybe a head-on collision. Maybe we have a head-on collision with this car. What will happen is this car will stop. It will momentarily stop, or else it will stop. When it stops, by the first Newton's law, we know that we should actually continue moving. An object will continue moving unless a net resultant force acts upon it. So this object will continue moving even though this car is stopped. So when these objects continue moving, there is a windscreen here. This guy can be thrown out of this windscreen, or else he can smash himself on this windscreen. That means that he will get injured through that. But however, this safety belt is applying a force that is going that side. So let's hear what they're asking now. This precaution is an application of which one of the following physics laws? Definitely it's an application of what? Newton's first law. Because we are saying that the safety belt will apply a non-zero resultant force that will cause this object to change his state of motion. Because we said this guy will be thrown out of this window or out of this windscreen if there was no safety belt. Because from Newton's first law, he will continue moving unless there's a force that stops him. That force is the force that is applied by the what? By the safety belt. So this is an application of Newton's what? First law. Now that marks the end of our what? Of our multiple choice questions. Now we want to start on our structured questions. So multiple choice questions carries 20 marks. So 20 marks is a lot for someone to be guessing. Let's try by all means to use our what? Our physics laws, guys, to actually get to choose the correct and most accurate answer. Now let's go where we are now actually supposed to be using our reasoning. Now, a 600 Newton force is applied horizontally on a block of mass mkg by means of a massless inextensive rope. The block remains stationary when the angle that the rope makes with the horizontal is 30 degrees. So this is the force that is being applied. It is being applied in the horizontal direction. That is 600 newtons going that side. So it means that this force is having an effect of pulling this object that side. But because this object is actually what? Is actually hanging through an inextensive rope. So you are going to have some tension that is at a certain angle. So this tension would be in that direction because this tension is trying to pull back this object. So it would be in that direction. And now, if the tension is in that direction, it simply means that we are going to have the horizontal component of the tension, which is Tx, and the vertical component of the tension, which is Ty. At some point in time. Now, let's hear what they are telling us, or else what is it that they expect us to do there. Explain why the block is stationary. Why is the block stationary? It simply means that whenever something is stationary, there is what? There is equilibrium. The block is stationary because forces acting on the block are in equilibrium. The forces that are acting on the block are in what? Are in equilibrium. Someone can say that the net resultant force is equal to zero. The net resultant force acting on the block is equal to what? To zero. This simply means that all the forces that are acting, so you can say all the forces acting on the block are in equilibrium. That's why this block is not moving. As long as we have got a stationary object, whenever we have got an object at rest, it simply means that F net is equal to zero because there's no acceleration there. It simply means that all the forces that are acting on the board are equal to zero. That is where we are saying all the forces are in equilibrium. That is what it means. Whenever an object is stationary, it simply means that that object is in equilibrium. Now they are saying use either calculation or construction to determine the tension T in the rope. Use a scale of 1 centimeter as to 100 newtons. Okay. I'm not going to draw, but instead I'm going to use calculation. That is the most easiest that you can actually get to adopt. Because at some point in time when it comes to drawing, some people, they might be vexed there. So let's use calculation. What is the magnitude of our tension? How do we find the magnitude of our tension? We are told that our block is stationary. Hence, therefore, the forces acting on this block are in equilibrium. Meaning to say, if I'm to look on the horizontal forces are in equilibrium. Net force on the horizontal force on the horizontal plane is equal to zero. If I look on the what? On the vertical force, net force on the vertical force, on the y, on the x, they are all equal to zero. So now, I'm going to look on the what? On the net forces that are acting on my horizontal direction. This is equal to zero. And this can be given by sum of all what? Horizontal forces. And what are my horizontal forces? I have got this force that is going that side. That brings the applied force. And then I've got my component of my tension that is going that side. So here I've got, let me take going to the right to be positive. So my positive direction is that one. So I will take my F applied to be positive plus the negative T of X. And these are equal to 0. And then I'll come here and say, let me substitute what I know. 0 is equal to force applied, it's what? Force applied, it's 600 newtons. Minus, what is my tension? My tension is the what? Is the horizontal component of this. So here you see that since this is actually 90 degrees, this is 30, this is going to be 60. And then if I look into that, I have got some Z angles here. This angle and that angle are equal. So this angle is going to be equal to what? To 30 as well. And this would be 90 degrees. So now, if I resolve these forces, I would have to say this is my what? My vertical component, and this is my horizontal component. And my horizontal component will be equal to what? T cos 30. So now I'm now saying T cos 30 is equals to 600. And then I can find my tension there. Okay. So let me just get to rub everything that I've said here so that we can find somewhere neat to do that question. so that at least people, they can actually get to follow neatly on what I'm doing. So here we say that the object is not moving because it is in equilibrium. So if it is in equilibrium, it means that F net is equal to 0. So now, F net in all direction is equal to 0. So now let's say we want to calculate the tension here, this tension, by calculation. So I'm going to use what? Calculation. So here I would say I'm going to look on the horizontal component. Here I would have Tx. This tension, since here you'll be having 30 and 90, this tension would have its vertical component, which is T in the Y and T in the X. And I'm saying that F net in the X direction, which is in the horizontal component, is equal to 0. But we know that F net in the horizontal component is given by the sum of all forces that are in the horizontal component. So it's more like we are saying 0 is equal to F1 plus F2 that are in the what? In the horizontal component. And what becomes my F1? I have got this force, that is the F applied. And then I have got that force, that is the, so now I'll take positive, I'll take going to the right to be positive. So this one is carrying a positive what? A positive direction. So here I would have F applied minus T of X is equals to 0. So I can say that T of X will simply be equal to what? To F applied. And what is my F applied? This is 600. And what is my T of X? I know that T of X is equal to what? T cos 30. And then I know that this is equal to what? T sine 30. So I will take this one being equal to what? To T cos 30. So how do I find my tension there? I'll divide throughout by T. I'll divide throughout by T there. So maybe I'll take this one this side. Let me take this to that side. So it will be T is equals to what? 600 divided by cos 30. And what becomes my value there? Now, this is the time where I take my calculator and I use my calculator. So, therefore, let's use our calculators to say 600 divided by what? By cos 30. 600 divided by cos 30. I'm getting an answer that is telling me that my T would be equals to 692.82. I've got a value of 692.82. So using my calculator, I'm getting an answer of 692.92. So my T becomes 692.92 newtons. That becomes the value of my tension by calculation. So that is simply how you do it. That is what you consider here. You consider the forces in the horizontal plane, and then you say net force in the horizontal plane is equal to 0 because the object is in equilibrium. And then now you consider the forces. You choose your positive direction, and then you sum those, you do the vector sum in your horizontal component, and then you find the unknown, which is T. After we are done with that, now they're saying, calculate the mass M of the block. Now, I now know that my tension here is equal to 692.92 newtons. And then I know that also going up and going down, we are in equilibrium. So I will take F net in the Y direction to be equal to. So I'll come here and then I would what? I would come here and then maybe I want to actually rub my board because we have already done this. So I'm just decongesting my board. So here we say that you would be having your T in the X direction. That we said it is given by what? T cos theta. And then T in the Y direction, that is given by T sin theta. So an F net is equals to Z, which is also given by sum of what? All forces in the Y plane. Now, let's look at forces in the Y plane. The forces in the Y plane, I can see that going up, it is given by that. So on my object here, what is going up is T of Y. What is going down is my weight. So I will choose, let's say, going down to be, going up to be positive. So this one will be positive, going up. So I would come and say Ty, which is a positive, negative this weight, which is a negative. And then when I have that, I would come and say, what is my Ty? I know that my Ty becomes T cos T sine of 30. T sine 30. This becomes T sine 30 minus what is my weight? Mg. And this is where I would be looking at that mass. And then this is equal to 0. Now, given that 0 would be equal to, I now know my T, which is 692.92 sine 30 minus my mass M, and my gravitational acceleration is 9.81. Given that, I can find now my mass by saying this. My mass times 9.81 would be equal to, I'm just transposing this to the other side. I've transposed this to the other side. So allow me to what? To transpose that to the other side. And then it becomes a positive. This remains as 692.92 sine 30. I will divide throughout by 9.81, divide throughout by 9.81. And then 9.81 to 9.81 is 1 times m. We are just left with m. So my m there would be 692.92 sine 30 divided by 9.81. When I do that, what is the value that I'm finding? You get to see that the value that I'll find, I'm going to find my mass as 35.35 kgs. So let's use our calculators, guys, to actually get to calculate our what? Our m there. That is what you're supposed to do there. Now let's go to question number 3. Learners conducted an investigation to determine the relationship between acceleration and applied force. During the investigation, a mass piece which hangs vertically by means of an inextensible string that passes over a frictionless pulley is used to accelerate a trolley across a horizontal surface as shown in the diagram below. Four different mass pieces were used to obtain 4 sets of what? Of readings. So this is the diagram, and this is the trolley. So we're using this mass piece to try and actually get to what? To apply some gravitational force there that will pull this trolley this side, so that we can be able to examine what? We can be able to examine the relationship between acceleration and applied force, where this applied force becomes our tension. So applied force is due to this mass. So this is where we are getting our applied force. So our applied force will be due to the weight of that what? Of that mass. So that weight is applying a tensional force due to this string that is connected to this trolley. So this tension becomes our what? Our applied force. And we want to see the relationship between this applied force and what? And the acceleration of this object. What would be the relationship between these two? That was the what? The investigation there. What would be the relationship between these two? If that is the case, they are now saying a ticker timer and tape are attached to the trolley in such a way that as the trolley moves, the ticker timer makes dots on the tape. The tape is used to analyze the motion, and the learner's results are plotted on a graph as shown below. So this is the graph that we are given. And from our results, the graph is showing us that this is force and this is acceleration. And from the look of the graph, we can see that there is a straight line relationship between force and what? The acceleration. Our force, this force is the applied force that we are looking for. And then you can see that the applied force is not starting at what? The graph is actually not starting at 0, 0. Meaning to say that we have got to say we have applied a certain force that might be equivalent, maybe let's say to 0.2 here. But the object did not start moving by that time. You have got your trolley, and that trolley is connected to this mass by a light inextensive string, and then you put a mass that will give you a force being equal to what? To 0.2 Newton. And this trolley does not move. What does it tell you? It tells you that there is an opposing force of motion that is making sure that this tension does not have any effect on this. That's why here there is no movement. Because whenever there is no movement, F net is equals to 0. So we are saying that there is an opposing force of motion somewhere, somehow. And since there is nothing this side, we would assume that that opposing force of motion is due to this surface. So it can be the frictional force. We can say it is due to what? To the frictional force. So I'm sure this value would represent our what? Our maximum frictional force. Or else, yes, after maximum frictional force, we start having what? Kinetic frictional force. So up unless we overcome this value, that's when our object will start moving. So that becomes our maximum what? Frictional force. Once we overcome that value, then our object will start moving. Let's hear what the questions are saying. I'm just interpreting these results from what we know. For this investigation, write down the conclusion of the learners. The conclusion of the learners can be to say the applied force is having a relationship that is directly proportional to the what? To the acceleration due to this linear relationship. Or else you can actually get to say that there is a linear relationship between the applied force and the acceleration. Because the investigation was how does the acceleration vary, or else how does the force applied vary with acceleration. So we have seen that the acceleration is directly proportional to the what? To the force applied at some point in time. And then they're saying, for this investigation, write down an expression to calculate the net force acting on the troll. Now, allow me to just get to wrap these things. The relationship that you can find here, the easiest relationship that you'll find here from this graph is a straight line relationship. So a straight line graph is given by the equation y is equals to mx plus c. This is our straight line. And this straight line graph can be given by that equation. Now, we have got force and acceleration. How can we represent that force and acceleration in this format? Definitely we need to have a net force, because I said that you can see that the object that we are trying to pull, which is our troll, is not moving, even though we might have some mass here that is pulling it downwards, is not moving. When our force is what? Our force is 0.2. There is no movement. So therefore, we are saying it might be due to that. So we are saying there should be what? Some frictional force that is opposing that motion. So what is causing this object not to move? It's because the net force is equal to 0. So at some point in time, our y should be in representation of what? Of our net force. So that that net force can be equivalent to 0 at some point in time. When what? Our acceleration is 0. Can you see that? When acceleration is equal to 0, that net force would be equal to what? To 0. Okay, fine. If that is the scenario, how do I now get to incorporate this y-intercept? How do I incorporate this y-intercept? Okay. I can now get to say, let me say that here I will now remove F net, because if I say F net, it will not make sense. So I'm saying that on my Y, I'm having my force applied. And then on my x-axis, I'm having acceleration. Therefore, this will be my mass. And then I've got a y-intercept, which I'm calling C. It's what? It's my frictional force. So I would simply say that F applied is equal to, this is actually coming from what? From this. This is actually coming from that. So here I would say that my force, this force, would be equal to what? To the F applied plus the frictional force. Whenever the force that is applied plus the frictional force, yes. So maybe I will say the F applied is mg, because what I'm applying is the weight of this. So I would say mg plus Fr. That should be equal to what? That should be equal to my force on the y-axis. Let me repeat that, because at some point in time, I might have said a lot of things that would end up confusing people. We are saying that the relationship between the graph that we are given is that of a what? Is that of a straight line graph. And we know that a straight line graph is given by y equal to what? To mx plus c. Now, from this graph, without thinking, cracking our heads much, from this graph, let's just use this graph to interpret and give the relationship. I have got my force on my y. So I would use that force on my what? On my y. Let me do this. I will use that force on my y. That is my y axis. On my x axis, which is this one, I have got my acceleration. That is my acceleration. And then this m, I will leave it like that to represent gradient. To represent gradient. This is representing my what? My gradient. So I'll leave it like that for now. It represents gradient. Plus, what is my y-intercept? I say that because the object is not accelerating, it is at zero at some point in time. This might be due to a balance between these two forces. And we said a balance between these two forces might be due to frictional force. So I'm saying that this is equal to my frictional force. So I would have my frictional force here. Now, where am I going to get this gradient? Now I would look at my graph. My graph, I have got F that side. My gradient can actually be equal to change in F. All over, I've got acceleration, change in acceleration. This is simply saying force over acceleration. And we know that from Newton's second law, F net is equal to mass times acceleration. So my mass is the one that will be given by what? F net divided by what? By acceleration. So in relationship that gives you force over acceleration, gives you your mass. So here, I would actually get to say I have got F is equals to my mass times my acceleration plus my Fr. So the relationship that I would have, or else the expression that I would have to calculate the net force acting on the trolley now, will now be to say F net is equal to mass times acceleration, the acceleration of this object that is going down, the acceleration of this object that is going down, that is going to be equal to g, that acceleration. So the expression there would be equal to mass times gravitational acceleration plus my frictional force. That can be the simplest what? Expression that I can use. Now, give a reason why the graph does not start from the origin. The reason why the graph is not starting at the origin is because we have frictional force. We have frictional force. That is why we are not starting at origin. That's why we are saying F net is equal to mg plus our frictional force, where this mg becomes our F applied. So we are not just having our force applied for the net force. We are not just having the what? The force applied. But the force applied plus the frictional force is when now we are now having our what? Our acceleration. So the reason why we are not starting at 0, 0 is because we have frictional force. So that our net force would be given by force applied by plus frictional force. So we need to start where now this value of our net force is greater than this two. What physical quantity does the intercept on the vertical axis represent? We said it represents what? We said it represents our frictional force. The y-intercept, we said it represents our frictional force. That is the only thing that is making sense. That is the logical thing that is making sense. To make sure that our trolley is not accelerating when we are having a rope that is connected through a frictionless pulley to a mass. This mass is pulling us down, so this trolley is supposed to be accelerating in this direction, but however it's not accelerating because F net would be equal to 0. Why? Because there is an opposing force, and that opposing force becomes what? The frictional force. That becomes our y-intercept. I'll keep on repeating that so that people they can have an idea from that investigation. What physical quantity does the gradient of the graph represent? Delta F over acceleration will give us mass. So gradient represents mass. Now they're saying use the information from the graph to calculate your mass. So the information from the graph, I would say 3.5 here, would be to say my mass is equal to the gradient of the graph. And what is the gradient? Change in F over change in acceleration. I'll pick 2 points there from my graph. From my graph, I'll just get to pick 2 points. So allow me to wrap these things so that I can pick 2 points there. And you can actually get to see the 2 points. So the 2 points that I'm going to pick, I can choose, let's say, to pick what? I can choose to pick this one. This point, I can choose to pick this one because I have the y value, I have the, gradient is given by y2 minus y1 over x2 minus x1. So I'm looking for y2 and y1. This becomes my point 2, and this can become my point 1. My y2 now, this is y2. This is my y1. This is my x1. This becomes my x2, which is this value. Now, my y2 becomes what? 1.20, 1.20, minus my y1 becomes 0.4. What is my x2? My x2 is this one, 0.2 up to 0.3. So here it's 0.25. So we have 0.25 minus, this is 0, 0. So generally, I'll be having what? 1.20 minus 0.4 divided by 0.25. That becomes my gradient, and that becomes my what? My mass. That is how I calculate my mass there. And if I use that to calculate my mass, let me enter my calculator. Let's use our calculators. That value should be equal to what? That value should be equal to 3.2 kgs. If I say 1.20 minus 0.8, it's 0.8, 0.4 is 0.8 divided by 0.25, that becomes 3.2. That is how I calculate my mass. So my mass here was just going to be equal to 1.20 minus 0.4 all over 0.25. And the value of the mass was going to be equal to 3.2 kg. That is the answer for that. Now, 3.6, the learners conducted another investigation using a trolley of a larger mass than the trolley used in the first investigation, but made of the same material. How does the vertical axis intercept of the graph of the second investigation compare with that of the first investigation? Is it less than, greater than, or remains the same? So we say the vertical intercept is the frictional force. Now, I'm now having a greater mass. Now let's look at how we calculate our frictional force. So for 3.61, we know that frictional force, which can be Fr, Fk, or else Fs, can be given by mu times the normal. So the normal on my object there that is traveling this side is balanced by the weight of this object. Now they are saying that the learners conducted another investigation using a trolley of a larger mass. So the trolley is the one that is having a larger mass. So the mass of this trolley is now great. So how do I find my normal force? My normal force is balanced by weight. So here I can come and say my normal there, I would represent my normal with what? With mg. So if m increases, my frictional force would also get what? To increase. So this one would be a greater value. We are going to have what? A greater value because my mass has increased. Explain your answer. The explanation that I just gave here. Maybe let me just get to give that explanation. Let me rub through. Frictional force is dependent on what? On the normal force. You will say frictional force is directly proportional, or else is proportional to the normal force. Therefore, when we increase the mass of the trolley, the normal force acting on it also increases. Thus, the frictional force will increase. So what we are saying is our frictional force is directly proportional to the what? It's directly proportional. This is proportionality relationship. My frictional force is directly proportional to my normal force. And my normal force is directly proportional to my mass because it is given by mg here. So as the mass increases, the normal force increases. Therefore, the frictional force increases. So we are going to have a what? A value of the x-intercept being a greater than the one that we had initially. That is simply how you have to reason there. That is how you have to reason. Now let's look at question number 4. Two blocks of masses 8 kg and 2 kg are connected with a light inextensive string and placed on a rough horizontal surface. When a force of 62 Newton is applied to the 10 kg block at an angle of 25 degrees with the horizontal, the system accelerates as 3 meters per square second to the right as shown on the diagram. The 2 kg block experiences a constant frictional force. So let's look on that diagram and the question that follows. So here they are saying that these two objects, they accelerate to the right with an acceleration that is equal to what? 3 meters per square second. And they are saying that this object experiences a frictional force that would be in that direction. That is equivalent to what? So that frictional force can be kinetic frictional force. That is equivalent to 2.1 newtons. Now they're saying state the Newton's second law of motion in words. This is where you would come and say, I would have wanted to represent, yes, that frictional force. I know that it acts. So that frictional force goes in that side. So I've got a kinetic frictional force, which is equals to what? 2.1 newtons. But however, now I want to define our state Newton's second law. You would say that if a net resultant force acts on an object, the object will start to accelerate. The object will start to what? To accelerate. And the acceleration of the object, it will start to accelerate, comma, with an acceleration that is directly proportional to the net force applied. And inversely proportional to the mass. Now I'm seeing that my answer won't be able to fit here. I should have just used some space maybe. Let me just get to say, let me use here. Right. I would say this is what? 4.1. And we are, so you say that Newton's second law states that if a net force is applied, if a net force is applied to an object, the object will start to accelerate with an acceleration in the same direction as the force applied and directly proportional to the force applied, but inversely proportional to the mass of the object. Mass of the object. So that is what Newton's second law tells us. And this is the law as a formula. We are saying that whenever we have got an object, and that object, on that object, you apply a net force. If a net force is applied on this object will start to accelerate. And the acceleration will be in the same direction as the net force. But however, you see that that acceleration will be directly proportional to the what? To the net force applied. But the acceleration would be inversely proportional to the what? To the mass of this object. To the mass of this object. Mean to say the greater the mass, the smaller the acceleration. That is what Newton's second law tells us. That is what Newton's second law tells us. So that is how you would have just what? Stated the Newton's second law there. Now they're saying draw a free body diagram of all forces acting on the what? On the 8 kg block. All forces that are acting on the 8 kg block. I would say that the forces that are acting on the 8 kg block now, I have got my weight due to that mass. I've got my normal force due to this plane or to that surface. I've got my tension. So this is normal force. And then I have got frictional force due to the surface. So I would also have what? Kinetic frictional force as the object is moving. I would have the vertical component of this force and the horizontal component of that force. So I would have F in the x direction and F in the y direction. Or else I can just have F applied there. So if I want to represent that as a what? As a free body diagram, I'll simply come and draw a dot to represent my object. I'll draw my normal force. I'll draw my weight. My weight is always directed downwards. I'll now draw my tension. I'll draw my frictional force. And then I'll draw my applied force. My applied force, like that. So this is the applied force. This is the applied force. This is the normal force. This is the normal force. This is the weight. And then this is the tension. This is the tension. This is the frictional force. This is the frictional force. And 5 marks gives you a hint of the on the number of what? Of forces that you're supposed to draw there. Okay, fine. Maybe allow me to just get to wrap these because we have already done them, so that at least I won't be having things which are just popping out, and disturbing our peace. Okay. Since that is the case, and now we have got our, what, our free body diagram, calculate the tension in the string connection. Calculate the tension in the string connecting the two blocks, right? The tension that we want to calculate is this tension that is between these two. So the tension can either be in that direction if we are looking on this object. It can either be in that direction if we are looking on this object. So what I'm going to do is, since I have got this force that is going in that direction, and at some point in time, I would have my tension. These are the only two forces. And I know my acceleration. I will look on the forces that are acting on the 2 kg block only. So allow me to look at the what? At the forces that are acting on the 2 kg block only. So on this 2 kg block, I have got my frictional force that is going in that direction. That is my frictional force. I have got my tension which is due to the pull by this block. So my tension will be going. And I've got some acceleration in that direction, which I know to be equal to what? 3 meters per square second. If that is the case, I would come and apply F net is equals to mass times acceleration. Here they say state Newton's second law. Newton's second law now becomes a hint of the coming what? On the coming questions. So here we are applying Newton's second law. So I'm going to apply Newton's second law on these forces that I have just shown there. So allow me to do 4.31 aside here. We've already done that. Now, that is 4.31. And I'm saying F net in the x direction on our 2 kg block. So I'll say forces acting on 2 kg. Forces acting on the 2 kg block. I would say the net force in the x direction is equals to 0. And then I know that that net force is calculated by the sum of all vector forces in the x direction. So, sorry, this is not equal to 0. Now, I'm now saying equal to 0. It is equals to mass times acceleration because we have this acceleration. So I'll say mass times acceleration is equal to, I have got two forces, which is to say my tension and my frictional force. Those are the two forces that I have. My tension and my what? My frictional force. I know my frictional force, I know my tension. So I'll take going to the right to be a positive direction because that is where my acceleration is going. So I'll say tension minus my frictional force. Now, what is my acceleration and my mass? My mass is 2 kg. My acceleration is 3. So I need to go back and look into the value of my what? My acceleration. Is the value of the acceleration equal to 3? We need to look into that. Yes, they said 3 meters per square second. So the value of my what? Of my acceleration there is 3. So you allow me to just get to remove that. That is 3 equal to my tension is what I'm looking for. I was given this value to be 2.1. So I'll just get to transpose this value to that other side. 2 times 3 it becomes 6 plus 2.1, that is equal to my tension. That is generally equal to 8.1 newtons. That is my tension. Let's look at the what? Second question. Now they're saying calculate the coefficient of kinetic friction between the 8 kg block and the surface. Now, you would see that they asked us to draw the free body diagram of the what? Of the 8 kg block. So now I'm now going to look on the what? That is for 4.32 forces acting on the 8 kg block. So the forces that are acting on the 8 kg block now are going to say net force in the x direction on the 8 kg block would be equal to what? Mass times acceleration, because we know this acceleration. And this is equivalent to what? Sum of all forces in the x direction within that block. And we drew a free body diagram that said, which was showing us something like this. We drew a free body diagram that was showing us something like this, where this is my tension, frictional force, and then my weight. And then I can now come and resolve this force into its components. So this force would have its x component. So I would say this is F. And then it would have its y component. And then I'll say that is Fy, where that is normal. So I want to look in the components that are in the x direction. Okay, fine. So in the x direction, I would come and say MA is equal to, I'll take going to the right to be positive, because that is where my acceleration is going. Fx, which is a positive, plus that are going the left, it's a negative t, plus a negative Fk. So I'll simply have my mass times acceleration, that is 8, times my acceleration, which is 3, equal to this force. What is that force? I was given that this force is equal to 62, and this angle was given to be equal to 25. If we look back at our diagram, these are the values. This force is 62 and this angle is 25. So that is what I'm just going to substitute there. I want us to see clearly what I'm doing here. So now, I would have this being equal to what? If I'm in this, this is going to be F cos theta. Now I would have 62 newtons cos 25 minus the tension. I said it's 8.1. I calculated that tension already. Minus the frictional force that I'm looking for, because I'm actually looking for the coefficient of frictional force. This can be given by what? I know that my frictional force, I know that my frictional force would be given by mu n. So I want this. So I'll know that that coefficient will be given by my frictional force divided by what? By my normal force. So I actually want to find this and find that so that I can be able to find that. Okay, fine. So let's finish up this one. And then here I would be having what? 24. So I will simply say 24. So maybe what I'm supposed to do is I'm supposed to transpose this to the other side and bring that on that side. So that I would have my Fk being equal to 62 cos 25 minus 8.1 minus 8 times 3, like that. So that I would be able to have the what? The value of my frictional force there. And what becomes the value of this frictional force? What becomes the value of that kinetic frictional force on my 8 kg block? Now I now need to calculate, so I would use my calculator then. The value of my frictional force is going to be equal to 24.09. Let's use our calculators, 24.09 newtons. Okay, fine. So this is equal to mu normal being equal to 24.09 newtons. So maybe let me remove the newtons so that I will not confuse people with these two ends. Okay, fine. Now I want this. So that would be equal to, I'll divide throughout by n, that is 24.09 divided by the normal force. This is the normal force that is acting on our 8 kg block. Now, let's go back to our free body diagram. Let's go back to our free body diagram. I would want to remove this. You will see that on this free body diagram, I'm also having a vertical force, which is Fy, that is going that side. So my normal force and my Fy are being balanced by the weight. That is what it is saying. So with that, let me show you what I'm actually referring to here. You see that if I use my vertical what? My vertical forces. So I'll say that F net in the y direction, that is to say, is equal to 0 because there is no movement in between. In my y direction, there is no movement. So this is equal to the sum of all forces in the y direction. Now, all forces in the y direction, I've got my normal force. Let me take up as positive. I've got my normal force there, plus my Fy that I have, minus my weight. So you can see that if I transpose this to the other side, I would have my weight being equal to my normal force plus my Fy. So that this normal force that I'm looking for would be given by what? By weight minus what? My Fy, which is equal to what? My normal force. So now, this is what I'm going to use. What is my weight? My weight is given by what? By mass times gravitational acceleration. My mass is 8 kg times 9.81. Minus my Fy, that is 62 sine 25, equal to my normal force. So the normal force here is given by that. So now I'm going to substitute that value for my normal force so that I can find my coefficient of friction. So here I'm going to come and say my normal force will be given by 24.09 all divided by my coefficient of frictional force here given by this divided by normal force, which is 8 times 9.81, which is my weight. This is my weight, minus my Fy, and we said my Fy is what? 62. It's 62 sine 25. And then the value that I find there becomes my what? My coefficient of friction. So if I do that and then I divide, I'm going to get 24.09 divided by bracket 8 times 9.81 minus 62 sine 25 close bracket. I'm getting an answer of 0.46. That is my coefficient of what? Of kinetic friction that is acting within the what? The 8 kg block. 0.46. That is mu. That is acting on the 8 kg block. Now, let's go back and let's see what they are now saying, or else what is it that they want us to find now? We now have the coefficient of kinetic friction that is acting on the 8 kg block, and we said this value here is equal to 0.46. The angle at which the force is applied is decreased to what? To 10 degrees. How will the answer in question 4.32 change? Right, only increases, decreases, or remains the same. So the answer here is for the what? For the coefficient of kinetic friction. Coefficient of kinetic friction is dependent on the surface of the plane is dependent on the surface. It does not depend on anything, but it depends on the what? On the type of surface. Let's say on the type of what? Of surface. On the type of surface. So it will remain the same. This coefficient will remain the same. It does not change because we are saying that the surface is not changed. Hence, therefore, the coefficient of kinetic friction will remain the same. Whatsoever calculation that we will do, it will give us the same value because the surface does not change. So you would say that it remains the same. Why? You say coefficient of kinetic friction depends on the what? On the type of surface. You are done. Now let's go to question number what? Let's go to question number 5. Question number 5 is saying that a satellite of mass 980 kg is orbiting the Earth at a distance of 160 kilometers from the surface of the Earth as shown on the diagram below. So here we are saying state Newton's law of universal gravitation in words. Newton's law of universal gravitation in what? In words. We know that the Newton's law of universal gravitation, I would come and write it here. 5.1. Every object in the universe, universe attracts, let me say that each object or every object, it's okay, in the universe attracts every other object with a force of attraction that is directly proportional to the product of the two masses and inversely inverse is I and inversely proportional to the square of the distance in between them, square of the distance in between them, or else the square of the distance between their two centers. It can be the square of the distance between their two centers or else in between them. So this is the law that gave birth to this. The net force of attraction, or the gravitational force of attraction, exerted by each body on another body is directly proportional to m1 times m2, where these masses are mass of object 1 and mass of object 2. But it is inversely proportional to the square of the distance in between them. Therefore, if I now come and then I say equal to, I would have a constant here. And that constant became the gravitational constant. And then I would have my m1 times my m2 all over what? R squared. That is how we came up with this law. To say that every object in the universe attracts every other object with a force of attraction that is directly proportional to the product of the two masses. This is the product of the two masses, and inversely proportional to the square of the distance in between them. This is the distance that is between their centers. So now let's see what is it that they want us to use that law for. Because the law that they want you to state on top usually becomes a hint of what they want you to do below. Now calculate the magnitude of the force that the Earth exerts on the satellite to keep it in orbit. So the magnitude of that force is calculated by this law. F is equals to what? G m1 m2 all over r squared. So we now need the mass of the Earth and then the mass of the satellite and then the distance from the center of these two. So now I will now need the radius of the Earth, so that I can add it with this distance, which is 160 kilometers. 160 kilometers is the same as what? 160,000 meters. I will add it with what? 160,000 meters. That becomes my R. And then I would also need the mass of the Earth, since I'm given the mass of the what? Of the satellite, which is equal to 980 kgs. And we know that the mass of the Earth is given by 5.98 times 10 to the power what? 24. Where do we get those values? We would be given an information sheet. And from that information sheet, that is where we get our what? Is where we get our values. And this is the information sheet. The mass of the Earth, let me say that the mass of the Earth, universal gravitational constant, G, is 6.67 times 10 to the power negative 11. We shall use this one. Mass of the Earth, M, we shall use this one. 5.98 times 10 to the power 24. Radius of the Earth, this one, we shall use it. So this is where you go and collect your what? This is where you go and then you collect your values, because we want to find this force of attraction, which is given by G m1 m2 all over r squared. Now, from the look of it, G, we have got mass of the Earth, and then we have got mass of the satellite all over the distance in between them squared. So it's the distance in between them what? Squared. So now I'm saying, from the values that are given there, we can simply come and say, I want to give an illustration of how we substitute those values, so that you know that when you are now in the exam, you just get to come and take this one, and then it becomes 6.67 times 10 to the power negative 11 times, what is the mass of the Earth? The mass of the Earth is this one, 5.98 times 10 to the power 24. And what is the mass of the satellite? It's 908 divided by, what is the radius there? We said the radius of the Earth. We need the radius of the Earth so that we can add to the distance that is what? That is given there. The radius of the Earth here, they've given us as 6.38 times 10 to the power 3 plus the distance, 160,000. So that is how you would find that force. And that force now, if I'm to punch my calculator, I should be getting a value of, if I'm to punch my calculator, I should get a value of, my value is 9,138, 98 newtons. That is how you use those values to calculate that force. So now I want us to return back to our question so that we can see how we would have applied it. Let us now return back to our question, and you get to see how we would have what? Applied it. Now I see that this is now misbehaving. Okay. And this is where we want to be. Right. So let me just get to wrap this. We have already used this. And now, since we have already used that, this is the law that we said we want to use. Now I'll explain again. the distance that we want is from here to there. So we would need the radius of the earth to add to that, so that it becomes what? If we add, it will become equal to r. And then we would need the mass of the earth and then the mass of the satellite, so that we can use F to be equal to G, mass of the earth, mass of the satellite, all over r squared. So now, because they said calculate the magnitude of the force that the earth exerts on the satellite to keep it in orbit. This is the force. We found that our G, from the values that we saw there, our G from the values that we saw, would actually want to erase a lot of things this side, so that when I'm now inputting my values, I won't be clumsing this. Okay. Right. I'll come and say the values that we found were 6.67 times 10 to the power negative 11. That is for G. And then for the mass of the earth, it's 5.98 times 10 to the power 24. That is for the mass of the earth. And then the mass of the satellite we are given is 980 kgs. We come and substitute 980 divided by the radius of the earth. They said it's 6.63. It's 6.3, not 63. 6.3 times 10 to the power 3. Yes, the radius of the earth is 6.38. I will add with 160,000 meters, because we want our radius in meters. We want it in meters. And then the force that I'm going to find, that's the one that I say that it is equal to what? 9,100 what? 38, 9,138, 98 newtons. That is the force there, which is equals to 9,138,98 newtons. Now, let's go to the next question. Calculate the weight of the satellite of the Earth. Now, how do we calculate our weight? Our weight is equals to what? Mass times gravitational acceleration. The mass of the satellite is what? 908. And our gravitational acceleration on Earth, it's 9.81. So that is what they wanted you to know that what is the gravitational acceleration on Earth is 9.81 meters per square second. So you will multiply by what? 9.81 meters per square second. And then the answer that you are going to find there, if you do that, you're supposed to find 9,604 newtons. If they'd given you maybe the moon, you would know that the gravitational acceleration on the moon is 1.6. That was the one that you have to use. So you know that the weight is calculated by what? Mass times gravitational acceleration, and then you substitute the values. Now, state three differences between mass and weight. State three differences between mass and weight. I would use a table here to say I've got mass this side, and then I'll have weight this side. What is the difference between mass and weight? I'm sure it is coming from, we said calculate weight, and you said weight is equals to mg. That is to say mass times gravitational acceleration. But mass is just given by m. So what is the difference between these two? The first difference is that this mass is measured in kgs, and this one is measured in what? In newtons. So this one is measured in newtons. And then this one does not depend on the location. This one depends on the location. Like I said, this G depends either we are on Earth or on Moon. So if G changes, our weight changes. So you will see that weight depends on location. Weight depends on location. Depends on location. Where are we? Are we on Earth? Are we on Moon? And then the other one is to say that this is the measure of the force of attraction that is exerted on an object by the what? By the earth. So this is the gravitational force of attraction exerted on a body by the center of, or else let's say, yes, towards the center of the what? Gravitational acceleration applied on a body, you can say by the earth towards its center. And then this one is the total amount. This becomes the total amount of object. Total amount of matter, sorry, in an object, total amount of matter in an object. So if we are having 10 kg rice, we are saying the total amount of those small, small what? Grains of rice are amounting to what we refer to as what? As 10 kgs. But when we say your weight, we are saying that the force that is pulling you towards the center of the earth is equal to. That's when you multiply this mass and the gravitational acceleration. So those can be three differences of what? Of mass and weight. Maybe to add another one as an extra, mass is a scalar quantity. There's no direction. This one is a vector quantity because it is directed towards the center of the earth, which is always directed downwards. So this one is a vector quantity, while this one is a scalar quantity. That can be another difference there. A vector quantity and a scalar quantity. Let's see now what becomes our last question. So here we are now doing question number 6, which is the last question for this. This is the last question for this question paper. Two identical point charges are placed 10 millimeters apart in a vacuum as shown below. So they are in a vacuum. The electrostatic force that Q1 exerts on Q2 is 8 Newton. So we know that the electrostatic force between these two charges is given by K, Q1, Q2, all over R squared. This is the one that they're saying it is equal to what? 8 Newton. Draw an electric field pattern between the two charges. They are positively charged particles. So definitely they are going to repel. Definitely they are going to what? To repel. They are going to repel these ones. And we know that the electric field always comes out of the positive to the negative. So you draw it going out of the positive, but in such a way that these ones are what? Are repelling. In such a way that they are repelling. Yes, the field has to go out of the positive charge, but the direction now, he has to make sure that these two are repelling. There is no attraction. There is no attraction. They have to repel like that. So that is how you would have drawn that. They have to repel. And then now, state Coulomb's law in words. Now, Coulomb's law is given by this law. We will now want it in words. What does that say in words? So you would come and say 6.2. Every point charge attracts another point charge with an electrostatic force that is directly proportional to the product of the magnitude of the 2-point charges. So here we are more interested with the word magnitude. You only multiply the magnitude of the 2-point charges and inversely proportional to the distance between their two centers, to the distance between the two centers of the point charges, between the 2-point charges. So it definitely becomes the distance in between the two centers. Now they're saying, so this is the law that gives you a formula which says what? F is equal to K Q1 Q2 all over R squared. So we are saying that the electrostatic force, this is the electrostatic force. The electrostatic force on a point charge, or else let's say every point charge attracts another point charge with an electrostatic force that is directly proportional to the product of the magnitude of the 2-point charges and inversely proportional to the what? Distance between. So if I say attract now, there are some which repels. So maybe we can say that the electrostatic force acting on a point charge due to another what? Point charge. So let me just get to say that the electrostatic force acting on a point charge, the electrostatic force acting on a what? On a point charge. So you come and say the electrostatic force, the electrostatic force acting on a point charge due to another point charge, comma, is directly proportional to the product of the magnitude of the 2-point charges and inversely proportional to the distance between the 2-point charges. So this electrostatic force that acts on another point charge, like that acts on Q1, would be directly proportional, act on Q1 due to Q2, it would be directly proportional to the product of these two charges and inversely proportional to the distance that is between those two charges. So that is what we are saying there. So that is the law that was stated by what? By Coulomb. Now they are saying calculate the magnitude of the charge. Calculate the magnitude of the charge. So let me just get to wrap this. We already saw how we're supposed to draw them. Now, on top here, I remember that I gave you that we are saying two identical point charges are placed 10 millimeters apart in a vacuum as shown below. The electrostatic force that Q1 exerts on Q2 is 8 Newton. So this electrostatic force that Q1 is exerting on Q2 is 8 Newton. And now they're saying calculate the magnitude of each charge. So Q1 and Q2, they said they are identical point charges. They are equal. So I would see that this Fe would be equal to KQ squared all over what? R squared, because the charges are what? Are identical. And this is what is equal to 8. And then what is the radius in between? 10 millimeters divided by 1000 millimeters. To make it in meters, that would be 0,01 meters. So that is the radius that I'm going to use. Now I'll come here and say, this is the same as, what is my K? I need to know the value of K, that is 9. The value of K from my information sheet, I know that K is given by what? By 9 times 10 to the power of 9 times Q2, Q squared all over 0.01 squared. Now, what I now need to do is to just get to solve for this Q. So that is what they were just asking me to do there. So I would come here and then I will wrap this so that when I wrap this, I can have enough space while I still have got my diagram near them so that at least some things can make what? Can make sense there. So here I'm just saying that I will keep my diagram there near with me so that I will say that F is equals to K Q1 Q2 all over R squared is equals to K Q squared all over R squared. So this F is 8 newtons equal to K, we are saying that it is 9 times 10 power 9 times. And then I then go to what is my Q is the one that I'm looking for. My Q is the one that I'm looking for. So it will be Q squared all over my R here. I've got what? 0.01. And if this is squared, then I can be able to make this the subject. Making that the subject, I will cross multiply by 0.01 squared. Cross multiply by 0.01 squared. This and that will cancel out. And then I will divide by that. I will then later divide by 9 times 10 power 9. I divide by 9 times 10 power 9. And I'll see that this will cancel with that. And then I'll be left with Q squared being equal to everything that is that side. So now, I'm now looking for Q. I'll just get to come and say 0.01 squared times 8 all over 9 times 10 to the power 9 is equal to Q squared. How do I find Q there? I'll just come and say what? Square root of that. And then I'll come and say square root of that. Then I can find my what? My Q. And what becomes the value of my Q? This is where I go to my calculator and then I punch in those values. And when I punch in those values, they are supposed to give me a value of, if I say 0.01 squared times 8 divided by 9 times 10 to the power 9 under square root, and then they are supposed to give me a value of 2.98 times 10 to the power negative 7. So they are supposed to give me 2.98 times 10 to the power negative 7 coulombs. So that becomes Q there. That becomes Q. So the magnitude of each charge, because we are saying Q1 is equals to Q2, which is equals to Q. That is to say Q1 is equals to Q2. That is equal to what? 2.98 times 10 power minus 7 coulombs. Now define electric field at a point. Define electric field at a point. I would come and say electric field at a point. Electric field at a point E is force per unit what? Point charge. So this is electrostatic force, electrostatic force acting on a point charge. Electrostatic force acting on a point charge at a point charge. So the electrostatic force per unit point charge acting on a point charge. So maybe I can actually get to write it correctly here. The electrostatic force per unit point charge acting at a point. Acting at a point. That is what electrostatic electric field. This is the definition of the electric field. Now let's go to the next question. Calculate the net electric field at a point P as shown on the diagram below. Now we want to calculate the net electric field at this point. So we are going to see that A point charge is always a positive charge. You have to know this. A point charge is always a what? A positive charge. So if a point charge is always a positive charge now, if a point charge is always a positive charge, what we are saying is this would actually get to what? To repel with this one. So this will push this one towards that direction. And this as well, it will push that same point charge towards that direction. So the electric field due to E1, due to Q1 would be E1, and due to Q2 would be E2. And then I'm going to sum these two. They'll give me my E net. I'm saying that point charge, I'm saying this charge would have an effect of repelling this point charge, and this charge would have an effect of repelling this point charge. That is to say, the force due to Q1 will be repelling this, the force due to Q2 will be repelling that. So the electric field, that is to say, E1 here would be in that direction. E2 here would be in that direction. And for me to find the net resultant electric field at this point, it will be due to Q1 and Q2. I will have to add because they are all directed in the same direction. They are all having the same effect. Now, what would be my E1? That would be F over Q, where I would say K, Q, 1, Q, all over what? Over Q. Or else I would have said Q1 there so that I can cancel out this. Now, let me do it neatly so that you would see how we get to electric field is given by force per unit charge. So that unit charge is, we are saying the charge at this point. So that becomes the charge at that point. So this force is given by G, is given by K, Q1, and QP all over R squared all over QP. That is the charge at what? At point P. So these ones will cancel out, and then I will be left with what? K Q1 over R squared. That is E1. E2, I would also have the same, but now here I would be having Q2. That is what I'm just going to do there. So, without wasting time, let's actually get to calculate that. Now, you would see that were we given the charges? Yes, we were told that we should calculate the charges, and we say that the charges are identical, which is to say we said Q1 is equals to Q2, and we said the value is what? 2.98 times 10 to the power negative 17 coulombs. So these are the charges that we are going to use. E1 would be equal to K, which is 9 times 10 to the power 9 times this 2.98 times 10 to the power negative 12 all over what? R squared, which is 0. Now, what is R for E1? So for E1, we are looking at the distance from this point charge to Q1 so that we can know the effect that E1 will have on this point charge. So the distance from here to there, that is 10 plus 5, that becomes 15 milliliters, millimeters divided by 1000 millimeters, that gives you 0.015. And then the distance from here to there is just 5 millimeters, so we are going to use that. So those are the R's that we are going to use. So here, my R is what? My R1 would be equal to 0.015 meters. My R2 would be equal to 0.05 meters. So those are the values that I'm going to substitute there. Now, I'm going to substitute 0.015 squared. What becomes the value of E1? Now, I would go to my calculator and say 9 times 10 to the power 9 times 2.98 times 10 to the power negative 7 divided by 0.015 squared. I'm getting a value of, I should get a value of 11,920,000. And I would be having what? Newton per coulomb, because this is force per unit charge. And then what becomes my E2? Now I can actually get to say what becomes my E2. My E2, because I've got the same charge, but here R was 0.015 meters. Now R2, we say that R2 is what? 0.005 meters. So E2 would be equal to 9 times 10 to the power 9, and then 2.98, because they have the same charge, negative 12, divided by the difference is the what? The distance in which they are acting, and then squared. And then E2 would simply be equal to, if I punch in my calculator, I should get a value of what? 9 times 10 to the power 9 times 2.98 times 10 to the power negative 7 divided by 0.05 squared. That should give me a value of 107, 280,000 Newton per coulomb. Now I'm saying that the net electric field will be equal to E1 plus E2. Why? Because they are in the same direction. That's why I will say they are both positive. So I'll just add them. So I'm going to have 11,920,000. And then I would add 107, 280,000. And then the total would be equal to 119,200,000 Newton per coulomb. That becomes the net electric field that is acting on the what? On the point charge P. Now, they are now saying that a third charge Q3 of magnitude 5 microcoulomb is now placed at point P. So at point P, which is this one, they've now placed a what? A 5 microcoulomb. Let me use a different marker so that at least you can see. They've now placed this 5 microcoulomb point charge. And then now they're saying, calculate the net electrostatic force experienced by point charge Q3 due to point charge Q1 and Q2. We now know E net that is acting upon this, and we say this is equal to what? 119,200,000 per Newton coulomb. And we agree that this E, we got it from force per unit what? Charge. Now, if that is the case, it's the same as I'm saying, I'm looking for this force, and I have that, and I know that, because this is what is given. So this is my E net, and this is my what? My Q. So I would come here and say 119,200,000 is equal to the net electrostatic force all over 5 times 10 to the power negative 6. Microcoulomb means what? Micro, it's 10 to the power negative 6. So times 10 to the power negative 6. Now I'm now just making my F the subject of the formula there. So I would come and cross multiply. By 5 times 10 to the power negative 6. Or cross multiply by 5 times 10 to the power negative 6. So this one will cancel out with that one. And then I'll be left with F equal to 5 times 10 to the power negative 6 multiplied by 119,200,000. And then I should be getting a value of 596 Newton. I should be getting a value of positive 596 Newton, which is the net electrostatic force. This positive means that this force is direct towards that direction, because that is where our net electric field was directed. So this force is directed in that direction. So that was it, guys, for our question paper. So thank you so much for being together on this question paper. Let's meet once again on the next coming question papers that I'm going to bring. I'll try by all means to bring different provinces and districts so that we can be able to have exposure and enough practice for our March test as we prepare for our March test. Thank you.